Hey Math 1, Mr. Zamudio here. Lesson 2.2, still dealing with sequences, arithmetic sequences, and geometric sequences. But today we're going to be talking about their formulas. So we have what is called an explicit formula. So we have an explicit formula for arithmetic sequences, and here's what that looks like. And we have an explicit formula for geometric sequences, and that's what this looks like. And we're going to be looking at what these formulas can actually help us do in a couple of examples. So first I want to talk about these specific parts of the formula. So looking at just the arithmetic one, there's kind of two main parts that we need to understand. I'm going to highlight these two. So we have this a sub 1 and we have this d. And what each of these means, this is your first term. So whatever is the first number of your sequence, that's what goes into that part of the formula. And this d, remember for arithmetic sequences, we have the common difference. For geometric sequences, it's going to be very similar. We are only going to plug in two things. It's going to be this g sub 1 and the r. And what g sub 1 is, you can probably guess, this is also your first term of your geometric sequence. And this r is the common ratio. All right. I don't expect, as of right now, you guys to understand what we just did. But I promise you, after we do these two examples, you have a much better understanding of what these explicit formulas are and what they look like. All right, so let's go ahead and get started with number 1. This first example, we have a sequence where we have 256, 64, 16, 4, 1, and so on. And what I'm going to do, and I think this is a good habit, is to first take this sequence and let's make it into a table. They even gave us a table right here so we can make. And remember, the term number, we know they give us 5 terms. So we have 5 terms here. And the term value, that's where I can put these numbers in. So my first term is 256. My second term, 64. And so on. Okay. So by looking at these numbers, the first thing really to realize is do we have an arithmetic sequence or geometric? Well, arithmetic, I'm going to check first. And remember, to check if it's arithmetic, what I can do is subtract these. Now, if I were to subtract these, watch what happens. 64 minus 256. So if I were to subtract these, I'd get a value of negative 192. And then if I keep going with this pattern, let's do 16 minus 64. We have negative 48. All right, I'm not even going to continue with this pattern because right away I notice we didn't get the same number here. So when I subtracted, we didn't get the same difference. So we don't have a common difference. So I know that this sequence is not arithmetic. I'm just going to write down here that it's not arithmetic. We didn't get a same common difference. So now let's check if it's geometric. And remember, to check if it's geometric, we do division. So in my calculator, I can do 64 divided by 256. So I'm going to pull up the calculator. Actually, I'm just going to do it on the side over here. But if you put 64 divided by 256 into your calculator, it'll give you 0.25. It may give you a fraction of 1 over 4, and 1 over 4 is the same thing, represents the same number, 1/4 or 1/4. And then let's continue with this pattern. Let's do, remember, the bottom divided by the top. So 16 divided by 64, 0.25. 4 divided by 16, 0.25. And if I did 1 divided by 4, this would also be 0.25. So in this case, we know it's not geometric, or it's not arithmetic, sorry, but we do have a geometric sequence, and we have a common ratio of 0.25. So I'm actually just going to say R equals 0.25. This is our common ratio. This is what we're multiplying by. So like as we see this sequence, we're just multiplying by 1 over 4 or by 0.25. And we know that that's happening. The numbers are getting smaller. Usually when you multiply by a decimal between 0 and 1, the numbers will get smaller. Okay, so that's honestly the hard part, guys. The rest of this is just filling in with stuff that we already know. So the hard part was figuring out, was this arithmetic or geometric, and what the common ratio is. We already have that now. So now this is just filling in with the points that we have here. So the point 1 comma 256, just fine. Here's 1 and 256 somewhere up here. There's 1 point. 2 comma 64, here's 2. 64 would be maybe right about there. 3 comma 16. 4 comma 4. 5 comma 1. This would be really small. We get this kind of curved shape, and if you remember, I talked that geometric sequences make exponential functions. So this actually turns exponential. Remember, those are your J or L shapes. And we're not going to connect these dots. Alright, I'm just going to label my graph here. I don't like having no names down here. So term number, that goes down here. And term value right there. Alright, almost done, guys. What we've done is we've taken a sequence, we've made that same sequence into a table, we made the same table into a graph. So right now we have 3 different ways to represent the same thing, and we're going to do the 4th way here. We're going to take these formulas and we're going to use one of them. Well, we know this is a geometric sequence, so I'm not going to use this formula. I'm going to use this formula. So geometric, G sub n equals this first term times R to the n minus 1. We're only going to plug in 2 numbers, and that's these 2 highlighted ones. So the first term, what was the first term of this sequence? Well, that was 256. So I'm going to plug in a 256 right there times R, the common ratio. What was the common ratio? Oh, we found that was 0.25. And then to the n minus 1 power. And here is a geometric explicit formula that represents this graph, that also represents this table, that also represents this sequence. These 4 things are actually the same thing. They just give you different forms. All the same thing, though. Alright, let's do the second one. I'm going to move a little quicker on this guy. So this one, we have 5 terms. 1, 2, 3, 4, 5. And I can see that they give you the 5 terms there. And I recognize the pattern right away. Maybe some of you can also. I can see that we're adding each time. So I'm pretty sure this is arithmetic. And again, to check if it's arithmetic, I could just do subtraction. So if I did 30 minus 12, 18, 48 minus 30, 18, 18, 18. So I know that this is arithmetic. And my common difference is 18. So we have D equals 18. All right, so let's just go ahead and plot these points. So we have 1 comma 12 will be about here, 2 comma 30, 3 48, 4 66, and 5 84. And let's label this with term number and term value. And if you notice, these arithmetic sequences, they don't make exponential functions, they make linear functions. And again, this graph, we don't connect these dots. These are discrete graphs. Sequences are discrete. Arithmetic sequences will give you a linear discrete function. Geometric sequences will give you a exponential discrete function. All right, and last thing, when it comes to writing the formula, you have to recognize which of these two am I going to use. Well, we had an arithmetic sequence, so I know I'm going to be using this formula. So A sub n equals, my first term. So what was my first term in this sequence? It was 12. Plus the common difference. We said it was 18. We're adding 18 each time. Times n minus 1. So I'm going to zoom in over here, n minus 1. And then this right here represents our arithmetic formula. So notice you can actually tell a lot from these two formulas. By just looking at this sequence or this formula, I can tell that, hey, we start at the number 12 and we're adding 18 each time. Or over here, we start at the number 256 and we're multiplying by 0.25 each time. All right, that's it for the notes for 2.2. You should have an activity or an assignment for 2.2 also.